All right. So where I left off in the last presentation, I was dropping a penny from the top of a building, which once again you should not do because you can kill somebody. So let's say I'm here. Here's the building. Here's the building. Here's the bad person who's going to drop something. And let's say they just hold it out and it just drops. The penny drops. So the penny is going to accelerate at the rate of gravity. So it's going to accelerate downwards at 10 meters per second squared. So let's start with an interesting question. After 2 seconds, so when t equals and let's say they drop it right at t equals 0, right? So after 2 seconds, how fast is it going? So time is equal to 2 seconds, or we could even say it is change in time, but we're assuming that we're starting at time equals 0, so time and change in time is the same thing. If time is equal to 2 seconds, how fast is it going to be going after 2 seconds? Well, let's use that formula. Velocity is equal to acceleration. Well, acceleration is the acceleration of gravity, so that's 10 meters per second squared. Velocity will be 10 meters per second squared times time times 2 seconds times 2 seconds. 2 seconds. Well, we can just velocity, we can multiply the numbers, you get 20. And then just like the numbers, you can treat the units almost like variables. This seconds is the same thing as this s, right? So this s is going to be in the numerator, and then you have an s squared in the denominator. So the s, at least this s will cancel out with one of the two s's that are multiplied down here, right? Okay, so we'll end up with, let me write it down. It'll be 10 meter seconds per second squared, right? And that's the same thing as 20. That cancels out, and this makes that 1, right? So that equals 20 meters per second. So hopefully you're starting to get a little of intuition why acceleration's units are meters per second squared. So after 2 seconds, we're going 20 meters per second. Now let me ask you a slightly more difficult problem that might have not been obvious to you. After 2 seconds, how far has the penny gone? Well, this is interesting. So we have this formula here. Distance is equal to velocity times time, right? But the velocity is changing the entire time. We know after 2 seconds the velocity is 20 meters per second, right? So we could call this the final velocity. So just call that v sub f. That's just a fancy way of saying final velocity. But right when we start at t equals 0, what was the velocity? Well, right when it started, the initial velocity, v sub I for initial, is equal to 0 meters per second, right? So what can we use this formula? Well, you might think of a way to already do it. Well, since the acceleration is constant, and you can only do this when the acceleration is constant, and in most of what you'll encounter in a first year physics course, the acceleration will be constant, and especially when you're dealing with gravity, the acceleration will be constant. You can actually take the average velocity to figure out the distance, right? So what was the average velocity over the 2 seconds? Well, my final velocity was 20 meters per second, and my initial velocity was 0 meters per second, and obviously I went kind of continuously over those 2 seconds from 0 to 20. So my average velocity, let's call that, actually I've never seen it done this way before, but let's just call it average velocity is equal to the final velocity plus the initial velocity divided by 2. I just took the average of the initial and the final, which is 20 plus 0, which is 20, divided by 2, which is equal to 10 meters per second. So when I just right when I let go of the rock or the ball or the penny, whatever I'm dropping, the thing is stationary. So it's at 0 meters per second. After 2 seconds, we used this acceleration formula. After 2 seconds, it accelerated to 20 meters per second. And over the course of those 2 seconds, its average velocity was 10 meters per second. So we can now use that average velocity in this formula right here. So the average velocity distance equals average velocity times time. You can kind of make a mental footnote. It's average velocity times time when the velocity is changing. And acceleration is constant, which is most of what you'll see and in most projectile motion problems. So now we could say distance is equal to the average velocity times time, which equals 10 meters per second times 2 seconds. Once again, the s's cancel out, so we're 20 meters. So after 2 seconds, not only is my velocity 20 meters per second down, right? Once again, if I said speed, it would just be 20 meters per second. But velocity is 20 meters per second down. But my distance is the ball or the rock, whatever, assuming no air resistance, has dropped 20 meters. So let's see if we can use that to, and hopefully that makes a little bit of intuition for you. And if you are taking physics, which you don't have to view these videos, that's the idea. I wanted to show you that this is actually exactly like one of the formulas that you will see in your physics class. And it's kind of a shame people tend to just memorize it in physics without in their when they're learning projectile motion without really appreciating that it just comes from distance is equal to velocity times time. And velocity is equal to, and actually before I said velocity is equal to acceleration times time, let me just expand that a little bit, because I assume that my initial velocity is 0. Let me just say that the final velocity is equal to the initial velocity, right? Because you could already be going, I don't know, 10 meters per second, and then you're going to accelerate. So the final velocity is equal to the initial velocity, this is an I, plus acceleration times time. Right? And we said that the distance, and we could rewrite this as the distance is equal to the average velocity times time. Then this, I just realized how funny that character looks. This is an I. This is an I. So the final velocity is equal to the initial velocity plus acceleration times time, and the distance is equal to the average velocity times time. So let's see if we can use these two formulas, which we essentially just applied in the previous example. We didn't do it exactly so formally, to come up with a formula for distance given acceleration and time. Well, we know that the average velocity, let me go here. Oh, I switched colors. The average velocity is equal to the final velocity plus the initial velocity divided by 2, right? Well, what is the final velocity? Well, the final velocity is equal to this. So we'll just substitute. So we have the initial velocity plus acceleration times time plus the initial velocity. My eyes are getting blurred. They're not showing up. These are all I's for initial velocity. It looks like a 2, but I think you get the idea. That's all initial velocity. All of that over 2. So the average velocity is equal to the initial velocity plus acceleration times time plus the initial velocity. All of that divided by 2. Well, that just equals 2 times the initial velocity. Now, that looks like an I now. Plus acceleration times time divided by 2. And that equals the initial velocity plus acceleration times time divided by 2. And this might be intuitive for you as well, that the average velocity is equal to your initial velocity plus, this is essentially the difference between the how much you're accelerating over that time in speed, but it's going to be that divided by 2 because we're taking the average. If what I just said confused you, don't worry about it. You could just backtrack into what we've said before. And you think about a lot of these formulas yourself and plug in numbers, and I think it'll start to make more sense. So we figured out that the average velocity is equal to the initial velocity plus acceleration times time. So we can just substitute that back into this original equation. And once again, I realized I'm running out of time, so I'll see you shortly.